So now we really are getting to the end of our discussion of parallel streams. We're going to start by talking about the benefits of parallel streams, and then we'll talk about some of the limitations of them in the next part of the lesson. So the Java parallel streams framework simplifies parallel programming by shielding developers from the details of splitting, applying, and combining results. By the way, does anybody know what these are shields of? Anybody here a Lord of the Rings fan? So if you're a Lord of the Rings fan, these are the shields of, I think, of Gondor or Aragorn or something. And this is the shield of Paul McCartney, which is kind of cool. So he's a Sir, right? He's been knighted by the Queen, or he was knighted by the Queen when she was alive. And so that is his shield, which is kind of cool. It's like a guitar, which I thought was neat. So often, parallel streams implementations will be faster and sometimes much faster and more scalable than sequential streams and loops. And here's some examples. This was on an older, actually no, I take it back. This is my current MacBook. 10 cores, 64 gigabytes of memory, 3.2 gigahertz. And you can see that the parallel implementations are much, much faster than the sequential implementations. Why is that? Because the tasks are independent, there's a lot of data, and the processing, looking up and finding the quotes, phrases from the works of Shakespeare take a while to compute. So parallelism is a good thing, and I've got lots and lots of cores too. As we talked about before, this is just a quick recap. Speed up will be a function of things like the partitioning strategy for the input. How well does it partition? How well can you merge things together? What's the amount of work performed? The number of cores? The input size? Blah, 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 blah. So n times q, that's a good thing to remember as a heuristic. Now, before you get carried away with like sitting down with your protractor and a calculator and like doing computations to see what n times q is it greater than 10,000 and so on, usually better just to benchmark your code and see. There's a heuristic that was described by Brian Getz where he says if n times q is greater than 10,000, then parallelism may be for you. But that's a heuristic, which means it's a swag. It's not necessarily going to be correct always. Another great thing about streams, and this will also be true largely of completable futures and reactive programming, reactive streams, is you don't have to put locks in your code, usually, and you don't need to put explicit calls to threads. You don't have to explicitly create threads. The explicitly creating threads thing is actually really helpful because who wants to have to futz with this low-level stuff? The synchronization stuff's a little bit more subtle, but the reason why you typically don't have to synchronize, usually, is because the whole idea of streams is to take the original data source and partition it up into chunks that can run independently, hence the embarrassingly parallel concept. And this feature, these features alleviate all kinds of complexities, both accidental and inherent complexities of concurrency and parallelism. We talked about the situation where you sometimes have to apply synchronization, where you're sharing something between the different threads that run in the parallel stream. For example, for the programming assignment that you're doing, we have the image cache that's shared, but that uses a concurrent hash map, so it handles the synchronization gracefully and very efficiently. You also want to have stateless behaviors wherever possible, make these things so-called pure functions, where they only depend on the input values and the output. There's no side effects, like updating a cache, but that's a way to be able to do this stuff. And if you really do need to share mutable state, use features from the Java class library. So there's a whole bunch of concurrency utilities, for example, shown here, like concurrent hash map and stamped lock and reentrant lock and all kinds of other things which you can use if you absolutely need to have them. Streams can help to make the code almost identical, usually identical with a few tweaks, which we've talked about, like flat map, which doesn't parallelize very effectively or at all. But usually the changes to go from sequential to parallel are minuscule. You change stream to parallel stream or some equivalent, and boom, everything's running faster if n times q goes the right direction. And we also have some other examples which we didn't really show here in detail where you can further parallelize things if you take control over the use of the stream support.stream factory method, which can be used to take a collection and its splitterator and then parallelize the collection, which is also super cool. Something else that I think is important is the synergy between functional and object-oriented programming. I just want to park here for 1 second. So what's really fascinating, if you've been in computing a long time, is you see trends and fads come and go. It's almost like fashion. So if you were not alive back in the 60s or 70s, but there was a period of time when wide ties were in vogue. And then the 80s came along and everybody was using skinny ties. So if you were wearing a wide tie in the 80s, boy, you were really not with it. You were uncool. And then all of a sudden again, like in 2005, wide ties came back again. So if you wait long enough and you keep your clothes in the closet, you can wear them again in like a decade or two when the fashion comes back around. Well, something is very similar goes on in computing, believe it or not. So for many years when we started out in computing, functions and procedures were the way to go. And there was lots of work in the 60s and 70s and early 80s on so-called structured programming, which was stepwise refinement and top-down design. And then people realized that they couldn't succeed with those technologies. They kind of programmed themselves into a corner. So starting, depending on what language you were using and what design paradigm you were from, but around the mid-80s, it caught on in vogue that object-oriented programming was the way to go. And my small talk friends get mad at me because they're like, we were doing this back in 1973. But whatever, let's ignore that for a second. I love my small talk friends, but they're always mad at C++ because C++ kind of ran away with the mind share in the mid-80s. So C++, C#, classic Java came along. That was object-oriented, and that was the cool new thing. And if you were doing structured programming in 1987, boy, you were a loser, just like somebody wearing wide ties. And then ironically, if you wait long enough, functional programming came back into vogue, which in some sense, I'm overgeneralizing here, I'm overstating this a bit, is a bit like the procedural approach back in the day, because now you're using functions as the basis of your design and decomposition and so on. And so what was interesting is now functions are hot, and if you're not doing functional programming, your language is old and broken, and if you're stuck with classic Java, you're a loser, and so on and so forth. In reality, and one thing that's funny is logic programming has always been extremely esoteric, except now we're doing machine learning, where now it's cool again. So if you wait long enough, everything comes back around. But having said all that, for my money, for my design dollar, I would rather use a combination of object-oriented and functional programming. And that's because object-oriented programming, despite some of its quirks, is still well-suited for structuring your programs, designing them in ways that allow them to be extended through inheritance and dynamic binding, which is still a very nice model. But where you do computation, it's often helpful to have functions. So it's the combination of Java's hybrid capabilities that really give it its modern power. By the way, C++, same basic idea, although they have variations on how they do it. C#, same basic idea. Python, same basic idea. God help us, JavaScript, same basic idea, although it's kind of lost in all the other noise from other quirks of JavaScript. So object-oriented design and programming give you understandability, modularity, readability, reusability, extensibility. That's really cool because we're focusing on structure and customization off of structure. And when you use functional programming, you can take the structure and then selectively override certain methods in order to be able to provide behavioral implementations of computation that are functional. So I like that combination. It's like peanut butter and chocolate, right? Peanut butter tastes pretty good, chocolate tastes pretty good, but boy, that Reese's peanut butter cup, like that's the bomb, right? Every once in a while I run into people who can't stand chocolate and peanut butter combination, but they're very rare. So if you don't like chocolate and peanut butter, think of something else that you might like better, like peanut butter and jelly or sweet and sour chicken or something like that. Okay, so that's the end of that discussion of the benefits of parallel streams. So now that I've told you about reactive programming as a concept, and I've told you a little bit about Java completable futures, let's see how those things compare and contrast and can be used, completable futures can be used to implement reactive programming. So the Java completable futures framework maps onto these reactive programming principles as follows. So first one is responsiveness. So remember, we want to be responsive. We don't want to block things. We don't want to keep the user interface code from being able to react to user events like touchscreen events or mouse events or GPS location signal events and so on. And the whole goal here is to avoid blocking the caller. Why do we want to do this? Whenever you block the caller, that will either underutilize the cores, because you're chewing up a core that could be used for something else while you're blocking, thereby impeding the inherent parallelism on multi-core systems or systems with direct memory access. And it also can complicate program structure for a whole variety of reasons that we don't have time to talk about right now. So that's one of the problems. The way to get around this in the completable futures framework is to use things like factory methods to start things running in the background, and arbitrary arity methods, which can be used to wait for a whole bunch of things to finish running asynchronously. There's other things as well, but those are two of the key ones. So we can have and completion stage methods. We can avoid blocking threads, which is the desired goal in reactive computing. There's also a quick assumption you need to be aware of. Reactive programming assumes that creating threads is expensive, and therefore you want to limit the number of threads, and you typically do that by having a pool of them like the common fork join pool, but not limited to the common fork join pool. Another goal is to avoid changing between thread contexts. So you might not want to have like a pipeline of threads that pass things back and forth to each other, because you're going to end up with too much context switching overhead, too much synchronization overhead, too much memory and cache management overhead. My PhD dissertation from many, many years ago talks about a lot of this. It was a long time ago at this point, but you might want to take a look at that. It's kind of fun. And so there's all kinds of cool ways that you can avoid changing threads by using the completable futures framework. There's some really neat methods. These non-async methods. There's the Java fork join pool. They all try to work very carefully to avoid having to change threads. Another important concept is resilience. So you want to make the methods that you write that run asynchronously resilient to failures. If anybody's ever seen Terminator 2, you know that the T-1000 Cyberdyne cyborg is able to take lots of punishment and survive until he's put into a vat of like molten metal or something like that. So you want things to be resilient and be able to heal themselves. And the way this is done is by having a really cool model of exception propagation in asynchronous contexts, which is super duper cool. Keep in mind, by the way, completable futures run in a single process, not a cluster, just like parallel streams, same basic thing. Another theme is elasticity. You want the computations to run scalably in a pool of threads that are themselves mapped to a set of cores. Once again, much like with parallel streams, we can use the common fork join pool or other pools. That's the main difference between the completable futures framework and the parallel streams framework. Completable futures can run in any kind of pool of threads, whereas parallel streams has to run in the common fork join pool, unless you do crazy things. And then finally, the implementation of completable futures is indeed message-driven. The programming interface is method-driven. You program by making method calls. But if you were to peek under the skirts of the abstraction, as we will do later, you will see that the completable future framework is implemented by creating messages and then passing those messages around, and ultimately having those messages stored and run in thread pools like the common fork join pool. And we'll take a look at that. So this allows you to get some of the benefits that you would expect with loosely coupled and isolated processing and so on, using message passing in the implementation part. As I mentioned before, that's a little bit different from, it's a little bit different type of a principle than responsive, resilient, and elastic. Those are really quality attributes, whereas message-driven is really an implementation detail that can be used to achieve other quality attributes like isolation, loose coupling. And if we start programming with modern frameworks for doing web programming like Spring, then you really can, in fact, start to program in a way where calls run in different processes in different computers by using the magic of asynchronous processing. We will not really cover that in this course. I'll mention it a little bit more later, but the course next semester will go into much more detail about that. So if this is interesting to you, feel free to take that course. Okay, so that is basically the mapping of completable future features onto reactive programming principles. Next time, I will also go through a more comprehensive comparison that walks through all the different Java programming paradigms, ranging from the original object-oriented model, where you only had one return value that was running synchronously. That's the classic object-oriented approach, to the parallel streams approach, where you can have a stream of things that run typically synchronously with parallel processing with common fork join pool, to reactive programming with completable futures in conjunction with parallel streams, and then to the pinnacle, which always occurs in the upper right-hand quadrant of any chart, which is the reactive streams model. And that's where we're going to head to next. But for now, we're going to talk about completable futures. Okay, so